let me talk about this application again. So we see a software prototype here that does automated tracking, in this case of cells. They're actually allowed to divide. But we have these parameters on the left-hand side. And when working on a new data set, I'm not sure if the appearance should be, this cost for appearances should be set to 1,000 or should be 1,100 or 1,200. I don't know what the cost for a missed opportunity should be, and so on. So in conventional tracking applications, you have the difficulty of hand tweaking these parameters. And if you now add more features, like what's the size difference or what's the difference in shape and so on, there is a parameter associated with all of these, and it becomes very hard to tweak these by hand. You could do unstructured learning, but that would ignore the constraints or the structure in your problem. So this works, it does something useful, but it's not what we really want to have. So you would like to get rid of this hand specification of parameters, and instead you would like to be able to provide a training set where you say this cell was that one and that cell was that one. So you want to provide ground truth annotation and then learn from this. So we want to use this kind of input plus these are the equations that we've just seen, only using different numbers, and want to be able to use that to learn the parameters associated with all these different features. And this is work that Xinghua Lu has been done. He used to be with this group, and he's about to join Microsoft now. And before the computer crashed, I had his picture up on the browser, but not now. Okay, so this allows you to find not just 6 or however many parameters you can still adjust by hand, but in this way you can easily set 30, 40, however many parameters you have. Here's again a representation of the problem. So there's the set of hypotheses. One hypothesis is that C1 moves to C1 prime, but there's another hypothesis that perhaps C1 moved to C2 prime, or perhaps that C1 divided into these two. And associated with each of these hypotheses is a binary random variable, and we have these consistency constraints. So down here are the consistency constraints. They work for division also if you use a somewhat more complete set of hypotheses. And there is your structured learning problem, where here the score has been written with an L. Okay, and then on a standard benchmark data set, it turns out that adjusting, so using more features than you would do conventionally and learning these in a structured fashion gives you much lower error rates than if you use fewer features or if you adjust the weights of these features by hand. So here, for example, is this large set of features, but tuned by hand rather than by learning the weights. And down here is a long list of the features, here difference in shape, difference in size, difference in the intensity mean, and so on. So anything that you can think of which somehow describes your problem. And for some of these weights, you can guess from the outset if their sign is going to be positive or negative. So for example, for an association to be true, the difference in position should be small. But there are others where it's not clear from the outset if you would expect a positive or negative contribution. And learning, well, it just finds those values for you given the training set. And as training set, you need these associations. However, the painful thing is that so here, for example, is a pair of frames. This is time t. This is time t plus 1. There are all the detections, and here the true associations are shown in bold. Unfortunately, it's a lot of work to annotate everything within the training set. So you would like to be able to learn from only partial annotations. And to that end, you can optimize. So this turns it into a structured learning problem with hidden variables. And then you can optimize, on the one hand, over all variables or over all configurations that are not consistent with the partial annotation. And you can optimize over all trackings that are consistent with a partial annotation. And each of the terms is convex, but in between them is a minus. So we have a difference of convex terms. And unfortunately, a difference of convex terms, is non-convex in general. And that makes for a very hard optimization problem. And it's only possible to solve this using an iterative heuristic. The one that's most frequently used is called convex-concave programming. And it essentially lets you fall into a local minimum. And if this local minimum is, so if your initial choice of parameters is decent, then you may find a good local optimum. And if it's bad, you may end up in a very bad part of parameter space. And in this plot here, you see that the error is a function of how much of the ground truth training data was used. And it turns out that, with a quarter or so of the full annotations, you get results that are on a par with learning that uses all annotations. So the horizontal line here shows you how good you get if you annotate everything as would be required in the formulation that we've seen together. And here, by the way, you see the difference between using a struct SVM and a structured perceptron. So the difference between the upper curve and the lower curve is if you insist on having a wide margin or not. Okay, time for a break. After the break, I will show you another application that your TA has worked on. Okay. So overall, we have seen a way to learn the parameters in, for example, a Markov random field in a supervised fashion by providing ground truth training data, combining pairs of structured input and structured output. If you want to read further, I want to advertise this booklet here by Sebastian Novozin and Christoph Lampert. They talk a lot about inference in vector graphs. So there are inference methods that we talked about and others that we did not mention, like dual decomposition. And they also give a brief discussion of structured support vector machines. And then I want to mention the work that Torben Kröger has done in the field. These are the predecessors. This was work of Björn Andres and Torben. The problem is to take 3D data like the one shown here on the top left. So you see a tiny 2D excerpt out of a large 3D data set, and you want to partition this into all the distinct units. And the units here happen to be dendrites of neurons. And if you look at this in 3D, this is a big spaghetti ball, pretty complicated. And you want to know where each and every one goes. And you see that the objects themselves, well, we can discern them because they are not in the same spatial location and they have a different shape. But there is otherwise nothing intrinsic that here would, in terms of texture or brightness or so, that would distinguish one process from the next. And this is perfect example of a problem that can be modeled as a correlation clustering uh, or multicut problem. There are two ways in which you could represent this problem. You could either say, after finding supervoxels, that's shown here on the top right. So we start with the raw data. We use elastic to find the boundary probability, and then the watershed to find supervoxels. All of this is in 3D. We could now assign a unique index to each and every supervoxel, as suggested here by the color coding. However, you need quite a large label space to do that. We do not have a 4-color theorem in 3 dimensions. So in 2 dimensions, we know that 4 colors would be enough to find or to represent any partitioning of a 2D image. But in 3D, that's not true. And the maximum number of colors you would need in the worst case would be the number of supervoxels. Now that's a very loose upper bound. In practice, you can do with much fewer. But anyway, so you want to, on the one hand, use few colors to work with a small label space, and on the other hand, you don't want to have 2 adjacent supervoxels to have the identical color, because then it would look like they are merged. So it means you need to solve the labeling problem at the same time, the graph coloring problem at the same time. Or you can use another representation, which is what we've done, where you associate with each of these boundaries between supervoxels a random variable that can be 0 or 1. And here 1 means the unary terms the classifier decided the boundary should be switched on. Purple means the classifier decided it should be switched off. And yellow means this classifier here has decided it should be switched on, but somewhere, this could be many slices on in the depth, the classifier made the opposite decision, namely that a boundary should be off. And then all of these yellow boundaries were removed by transitivity. So the advantage is we can work with a small label space. We only need 0s or 1s. The disadvantage is that consistency no longer is given automatically, but we have to enforce it. And that's shown here on the left-hand side. If you look at the 2 orange dots, they represent 2 supervoxels out of the many ones that you see. The boundary between these 2 supervoxels has been switched on. It's dark blue, so it looks like the orange dots should be in distinct segments. But somewhere here there is a path which connects these orange dots, which suggests they should be in the same segment. So we have a contradiction. And we need to forbid such contradicting situations. And the set of all permissible configurations lies within the multicut polytope, which has here been abbreviated as MC. And it consists of many inequalities, one associated with every loop in the data. And if you look at the dotted lines here, they form a loop. And we can now look at this inequality here. It says that one boundary along this loop must be less than or equal the sum of all others. So if we look at this random variable here sitting on the dark blue boundary, it is 1, but all the others are 0. So I have that 1 is less than or equal to 0, which is not true. And hence, this particular solution that you see here does not lie within the multicut polytope. It's not a legal solution. So to optimize the whole thing, you can write it formally here in just one line. Theta is a positive or negative number, which gives the penalty or reward associated with having a boundary switched on. So if it's a negative number, then the boundary would like to be on. If it's a positive number, then the boundary would like to be off. And Y is a collection of 0s or 1s. It's an indicator vector with one entry for each boundary, and theta are the corresponding positive or negative entries, the penalties or rewards. And we want to minimize this inner product here, subject to my indicator vector lying in this multicut polytope. So this is an integer linear program. The objective is linear in y. It's integer because I demand that y, all elements of y be 0 or 1. And then we have all these linear inequalities here, terribly many of them, which constitute the multicut polytope. Now you can use this, and this will give you consistent solutions like the one you see on top. And what I want to talk about now in the context of structured learning is how to find these parameter estimates, or these estimates, these penalties and rewards. So y, again, is a collection of all the indicators for all boundaries. Theta is a vector of all the penalties or rewards associated with having a boundary on. And so far, I pretended that theta was somehow just given. But now, really, we want to learn it in a structured fashion. And that we can do as follows. I can rewrite this vector theta as a product of a vector and a matrix. W is the vector holding all my parameters, and A would be a collection of all the features for all the boundaries. And by associativity, I can draw my parentheses here around these two terms rather than around those two terms. And then I can pretend that A times Y is my feature map. And this is now using exactly the same letters that we had when talking about the struct SVM. So I can express my problem as being linear in the parameters, and I can now learn the parameters by minimizing, again, the sum of a regularization term plus a loss, which is written out here. And this amounts exactly to the structured learning problem that we have discussed. So you can supply pairs of training examples, so of structured input and of the true output, if the boundaries should be on or off. And you can then use this to learn the parameters of your unary potential that will tell you if a boundary should be switched on or off. And this is straightforward if you do not use margin rescaling. It is also okay if you use margin rescaling using a loss function that you can solve at the same time as doing your normal inference. It becomes very hard if you want to use a loss function that does not allow the inference that you would normally use on the problem. And it is this added complication that Torben has addressed in a paper that will come out at MICAI later this year. So here's another application of structured learning. And if you do it, you can produce pretty pictures such as this one. I'm cheating here a little because this picture was produced without the structured learning. And so the quality of the segmentations that you get out is impressive, but not yet sufficient. So we're still making errors. We're still losing some of the very thin processes. And we're now working on bringing more shape knowledge to bear in order to hopefully get that problem solved also. So that's all I wanted to say about structured learning. Do you have more questions? It's currently a very active field of research where people look at different applications. So they want to see how can existing problems be formulated so as to make them amenable to structured learning. And it's also an active topic on the theoretical side to see what is the impact if you don't do this inference step where you look for the most violated constraint, if you don't do it accurately, but if you do it only approximately, which approximations work best in conjunction with the learning. Okay, so with this we are very, very close to the state of the art, in this whole field. And if you've understood a little bit of it, I will be happy and proud. I want to talk about what's on next week. Next week is the last formal lecture. I want to talk about computational imaging. That's an umbrella term for all techniques that at the end of the day give you an image, but do so strictly only by means of a computer. So having the computer is prerequisite for getting out an image on the other side. And there are some interesting techniques that fall in that realm. For example, there's the whole field of light field imaging and planoptic cameras. So in a light field, you measure not just how many photons are incident on a pixel, but also from what direction they come. So you acquire more information from your surroundings. And this allows you to do neat things like to refocus an image after the fact, or to move your camera to a virtual standpoint. And this has applications on the one hand in all of the entertainment industry, but on the other hand, I think this will make a big difference to the consumer market eventually, because in higher quality cameras and cell phones, you have moving parts to focus. And if you acquire the light field instead, you will no longer have any need for focusing or for mechanically moving parts. So I think that's one application that we'll see in the real world in the future. And I want to explain to you the characteristics of these light fields and how to process them. And there are other interesting tricks that one can do with the coded apertures, for example. I want to talk about those, and perhaps also about tomography. In tomography, we have a choice of either talk about what is done in X-ray tomography or in MR imaging.